So let's talk now about reaction enthalpy. It's the change in enthalpy that's associated with a reaction. Okay, so and delta H with the R subscript between the delta and the H is called, that's the official symbol for reaction enthalpy. You might see that symbol written as delta H RXN. Okay, so RXN is abbreviation for reaction, or you might see it as delta H RXN in between. But I'd like you to be familiar with this way of writing it because that is the way it's tabulated in handbooks. Okay, so that's a standard abbreviation symbol for reaction enthalpy. So reaction enthalpy is just the difference in the enthalpy of the products and the reactants. So imagine a fictitious process where you start out with your reactants separated from each other, okay, and then you mix them, and then the reaction happens, you make your products, and then the products are separated. So if you calculate if you were able to get the H for the separated products, you subtract the H for the separated reactants, that's called your reaction enthalpy. Okay, that's a fictitious process. For practical purposes, we can say that the delta H for that is in fact essentially the heat of reaction at constant pressure for some reactions. Okay, and that's why we give that symbol delta H of reaction it's synonymous with the heat of reaction. Delta H is synonymous with heat of reaction. Okay, let's clarify that. Okay, like I said, the delta H, the reaction delta H, the reaction enthalpy, okay, is equal to the enthalpy of the separated products, okay, minus the enthalpy of the separated reactants. But since enthalpy is a state function, okay, even though this doesn't actually happen, okay, you can just imagine it happening. What we can do is, like we did, what we do is we go to the lab and carry out this reaction right here in a calorimeter, okay? When you mix your reactants, you get mixed products in an insulated container. Q for that is 0. So delta H for that step is 0. Now you imagine that you let your products go back to the original temperature of the reactant. So temperature has changed from T1 to T2 as a result of the reaction. Now imagine taking the mixed products from the final temperature to the original temperature of the reactants. And we said in an earlier lesson that that is your heat of reaction, right? Now, imagine one final step where you unmix those products to get separated products, okay? The Q for that last step is going to be 0, okay? Only for reactions where the limiting reactant is 100% consumed. In other words, for reactions that pretty much go all the way to completion. Why is that? Well, imagine the reverse of this process right here. Instead of unmixing the products, okay, imagine a process where you're mixing the products. If the reaction goes all the way, what happens if you mix the products? Nothing, right? So delta H for the mixing here would be 0, so Q for the unmixing would be equal to 0. But that's only true if, in fact, the reaction goes all the way. In other words, if the reaction goes all the way to the product side, what you're saying is the likelihood of products reacting to give you back your reactants is very low. So the delta H for the unmixing, for the reverse process is going to be 0. Okay? So if you look at this diagram that we have right here, we can say that the delta H for the reaction, okay, the reaction enthalpy is Q1, which is 0, plus what we call the heat of reaction, which is minus C delta T, right, plus Q of unmixing, which is 0. So that's why we're saying that this, for practical purposes, we can say for as long as we're dealing with the reaction that goes all the way to completion, the reaction enthalpy is just equal to the heat of reaction at constant pressure.